This is going to be a video on density. We started to discuss density back in the very first chapter, chapter 3, when we were learning about physical properties. And at that time we learned a whole bunch of physical properties like color, like state, like ability to conduct electricity, if it's malleable, if it's lustrous, all those kinds of things. One of the things we talked about in that section was a substance's density. And basically what we had in our mind at that time was density was a measure of how heavy something was. And that still stands to be true. When we discussed it at the time, I said it's nice if you can think about a sample of something all the same size. So on this slide you can see there are 4 boxes. Each box is 1 cubic centimeter. You can see that it lists the density of ice to be 0.917, water to be a mass of 1 per 1 cubic centimeter. You can see that lead is 11.3 grams per 1 cubic centimeter, and osmium, a very odd pick for a metal, 22.5 grams per 1 cubic centimeter. Instinctually, you should know that the osmium will be the heaviest of those samples because it has the highest mass. I want you to remember the word intensive. We discussed intensive and extensive properties. An intensive property doesn't change based on how big your sample is. So for example, if I had a sample of lead that was much, much bigger, let's just say it was 1,000 cubic centimeters. Now that's there's no way I'm going to be able to draw, well I could, if I made my box much, much bigger, say 10 times bigger on each side, say 10 centimeters by 10 centimeters by 10 centimeters, the volume of that box would be 1,000 cubic centimeters. So that's 1,000 times bigger than the boxes above. If this sample, let's just say, was lead, the third one given in the diagram from your textbook, then it should instinctively follow that the mass of this piece of lead, which is now 1,000 times bigger in size, would be 1,000 times bigger in mass. So instead of being 11.3 grams, it would be 11,300 grams. Remember, intensive properties, it doesn't matter if you have a teaspoon or a truckload. When you divide the mass of your sample by your volume of your sample, the answer will always be a constant for each substance. So 11.3 grams divided by 1 cubic centimeter, that worked out to be a density of 11.3 grams per cubic centimeter. I took a larger piece of lead that had a mass of 11,300 grams and divide that by its volume of 1,000 cubic centimeters. It's still going to have a density of 11.3 grams per 1 cubic centimeter when I simplify my ratio down to lowest terms. So density is intensive. It does not matter how big it is. When you divide the mass by the volume, you will get a constant, and that constant is the same for that sample no matter what. Now, let's go to your booklet. Actually, before we do the booklet, I've cropped a piece on this slide that shows you what you have access to on your thick cardstock table, your yellow table I believe it is. The color doesn't matter, but if you look on this side, the one table that's up on this side, oriented up, straight up and down, is a table on densities. I'd like you to notice that there's a column for solids, and all these solids have densities listed as grams per cubic centimeter. There's a column for liquids, and these are measured in grams per milliliter. And there's a column for gases, and they are listed in grams per liter. Each one of those units though, is a mass per volume. So even if you forget for some reason the formula for density, this cheat sheet, this table you have, shows you that it's mass divided by volume by the simple fact of all those 3 units. They're slightly different, but they all have the same concept, mass divided by volume. Okay, in your booklet now, you're going to see a question that's going to come up. It's going to ask you, if you had 250 milliliters of water, 250 milliliters of homogenized milk, 250 milliliters of skim milk, and 250 milliliters of Pepsi, would they have the same mass? And that's a question that I never answered in my life until I was well into my 30s. My brother once said to me, I can't stand lugging in all that homogenized milk, which is a strange comment. But he was a merchandiser for Baxter Dairies, and his job was to bring the milk products from the back of the cooler at the superstores and Sobeys and all those kind of places out to the front cooler where the customers pick up their milk. He used to say the homogenized milk was so much heavier to lug around. And until I thought about that, I thought he was crazy. But it comes right down to the concept of density. One red milk carton, which most of us have a concept of, those milk crates, it can hold, say, 9 2-liter bottles of milk. If you had 2 red milk crates side by side, the homogenized milk is going to be heavier than the skim milk because it contains more particles, more fats inside that volume. Same thing when you look at this slide, comparing a can of Pepsi to a can of Diet Pepsi. The can of Pepsi is actually heavier than the Diet Pepsi. It'll sink in water, whereas Diet Pepsi will float. So they have the same volume, but they have different masses. Therefore, they're going to have different densities. So in your textbook, in your booklet rather, you're going to see these notes about formulas. So I want you to memorize from this point on that density is going to equal mass over volume. Now, density is simply a conversion factor. You can use density just like you would use conversion factor for molar mass or Avogadro's number. You can use that conversion factor to change from one unit to the next. Some people prefer, however, not to use the dimensional analysis method to solve problems. They like to use a cheating method, I call it, which is to allow you to rearrange formulas using kind of more of an equation method from math. And you can actually convert this formula to a triangle. I think many of you probably learned this in math. There's a summary formula, looks like a triangle, and it'll allow you to solve for any one of these variables. Looks like this. If you cover up the m, then you can find the mass by doing density times volume. Density times volume. If you cover up the v, what you're left with, the volume will be found by taking your mass and dividing it by your density. If you want to solve for your density, clearly we already know that's mass divided by volume. I don't necessarily like to use this method because then it basically turns into 3 different formulas that you sort of have to have an idea how they work. I prefer to use the one formula that I know, density is equal to mass over volume, and then do dimensional analysis and not have to think about anything. But we all have our preferences, I guess. So what I want to do now is I want to do some math questions that actually get you to calculate density. So for example, number 1, find the density of a piece of wood. A thin piece of wood, given its dimensions, are 6 centimeters by 5.6 centimeters by 2 millimeters. That's clearly going to be some kind of a cube type deal. It's not very thick, so I'm just going to draw a little picture to get you to visualize. To find the density, you should know in your head that density is going to equal the mass divided by the volume. We need to figure out the volume first. So we have a 6 centimeter long piece of wood, a 5.6 centimeter piece of wood, and we have a 2 millimeter watch your units, 2 millimeters. You should immediately know you're going to have to change your 2 millimeters into centimeters to be able to find your volume. Volume is going to equal length times width times height, if it's a nice perfect little cube like this. So 2 millimeters, if you have to go off to the side and do that in your head, or do it on paper, 2 millimeters, you need to divide that by 1,000. We'll divide it by 10 ultimately, I guess. 2 millimeters, there's 1,000 millimeters in 100 centimeters. So you're going to end up with 2 times 100 divided by 1,000. You're going to end up with 0.2 centimeters. So back to my volume formula. I'm going to take 6 centimeters, multiply it by 5.6, and multiply it by 2. And that's going to give me a volume of 6.72 cubic centimeters. I'm asked to find the density, so I go back to my formula. Density is equal to mass divided by volume. The mass is conveniently given to me in grams. So 0.873 grams divided by the volume of 6.72 cubic centimeters. Plug them into your calculator. You're going to get an answer of 0.1299, etc. grams per cubic centimeter. Now the question that asked you to identify, or I didn't ask you directly, but I want to know what kind of wood is it. So if you go to your density table, go back a page, your yellow table, look down the column. If you scan, you will see the very top list. It says balsa wood. Balsa wood has a density of 0.13 grams per cubic centimeter. So the identity of this sample would have been balsa wood. Densities are used quite often to identify unknowns. If you find the mass, calculate the volume, you divide them, you can say, oh, well, that substance is aluminum because it has a mass of whatever. Or that substance is gold because it has a mass per volume of whatever. A couple more questions in here to do on the next questions 2 and 3. So this question number 2 says, what volume in liters of chloroform would be needed if a procedure required 35.5 kilograms? So when I read that question, what I hear is I hear a mass, which is given to me in kilograms. That's a lot of chloroform. So I know that densities are going to be grams per something. In my head, I'm automatically changing that mass into grams, but I can do that properly in steps. What else I'm thinking is that chloroform, I know this from my life experience watching shows and stuff, the chloroform is a liquid, but if you didn't know that, you can go to your yellow table and look it up. The density of chloroform you'll find on your table is in fact a liquid, and the density is going to equal 1.49 grams per mil. So that means if you have 1 milliliter, it's going to have a mass of 1.49 grams. And I know my volume in liters, so I know that something's going to be a little off. So I write down what I'm given on the far left. If I do it, dimensional analysis method. 35.5 kilograms. I'm going to change that to grams. My yellow table says 1 kilogram is equal to 1,000 grams. If I get to that step, I'm going to have 35,500 grams. And I want to change it into a volume. I can use my density. My density can be arranged, like all conversion factors, one of two ways. The number on the top, number on the bottom. I'm going to write the grams on the bottom, so I'm going to say 1.49 grams is the equivalent to 1 milliliter for chloroform. So 35.5 multiplied by 1,000 divided by 1.49. And in the last step, the question asks for liters. So I'm going to write down that I know there's 1,000 milliliters in every 1 liter and do it that way. So 35.5 times 1,000 divided on the bottom by 1.49 divided again by 1,000 is going to give me a final answer with significant digits. I've got to round to 3 places. If you look at your calculator, it's going to say 23.8 liters is the answer. You could have also done that question using the rearrangement of the formula. You could have also taken the volume and taken your density. That's wrong. Taking your mass and dividing it by your density. If you rearrange the triangle formula, take your mass and divide it by density will give you volume. The mass is 35,500 grams. The density was 1.49 grams per milliliter. The answer to that would be the volume in milliliters. So it'd be like 23,825.5 mils. Then you have to do your last step and change it into liters. You would divide it by 1,000. You get the same answer of 23.8. It's just a different method to do it. And I'm not going to tell you what to do. I'm just going to present both ways. We've done both methods before, so it seems logical that you could pick one of those from whichever makes you more comfortable. I like the dimensional analysis method, but some of you don't, so that's fair. Question 3, we're asking for the mass. Mass is typically in grams. Chlorine, you should know, chlorine is a gas. And I bet you the density for chlorine is on the yellow table. It occupies a volume of 8.2 liters. If you go to your yellow table and you look up the density of chlorine, it's 3.17 grams per liter. Notice it's per liter. So if I start doing this question with dimensional analysis, I write down what I'm given, which is 8.2 liters. And I want to convert that into mass. Well, I have a conversion factor, density, that describes the mass per volume. On the bottom, I want my canceling unit. So for every 1 liter of chlorine, it's going to have a mass of 3.17 grams. So essentially, I'm going to take my two numbers and multiply them together. 8.2, the liters will cancel, by 3.17, and that'll give you an answer of 25.994, and that's grams. And that's too many significant digits, obviously, but that's the calculator answer. So 26 grams would be the mass of your sample of chlorine. And maybe you're thinking all along, how are you ever going to measure a volume of a gas on a scale? And it's not, you don't do that really. You measure the volume of a gas in liters, and you convert it to grams, either using density or, that's actually the most logical approach. You could also have used the formula mass is going to equal density times volume, if you want, or volume times density. If you wanted to use the triangle to rearrange, you could have just simply plugged in 3.17 grams per liter, multiply that by 8.2 liters, and you would get, of course, the same answer, 26 grams. The grams will be what you're left with. So on the next page is practice, and I want to draw your attention to number 4, because it has a very important concept in it that I have not mentioned up until this point. If you have a piece of metal that's not perfect, not a perfect cube or a perfect rectangular shape, then how are you going to measure the volume of an irregular shape? And that becomes a problem if you can't use a ruler. So what's the strategy? And the strategy is actually quite simple. Provided that piece of metal ore doesn't react with water, you can put it into a graduated cylinder. So picture, on the next slide I've got a picture of this being done. So my crappy picture will make more sense in a minute. Put a graduated cylinder, and this question says, a piece of metal ore weighs 8.25 grams. You can measure that easily enough on a scale. When a student places it into a graduated cylinder containing water, the level rises from 21.25. So say you put some water in there, And on the side of the cylinder, you identify that's 21.25 mils. You throw in the piece of metal ore, so it's a heavy rock, and the water level obviously is going to rise because you now have more material in that same space. It goes up to 26.47. So the displacement from 21.25 to 26.47, that extra bit that went up is obviously the result of adding the metal ore to the water. And if you subtract those two volumes, the final volume minus the original volume, you would get the difference in volume of the ore. How much the ore made the water line move up. So 26.47 minus the 21.25 would give you a difference in volume of 5.22 milliliters. So although that shape was very irregular, you can measure the volume indirectly by doing displacement in a water environment in a graduated cylinder. So now you have a gram, a mass in grams, and now you have a volume. You can find the density easily enough by using the formula density is equal to mass over volume. The only word of caution here is that you should probably remember that when it's a solid, the density should be reported in grams per cubic centimeter. So, 8.25 grams divided by the equivalent, which is 5.22 cubic centimeters. Remember, a cubic centimeter and a milliliter are the same measurement. If you divide those into each other, you're going to get a density. I don't have enough room, of course. Wasn't intended to be done. Anyway, doesn't matter. But down here, 8.25 grams divided by 5.22 is going to give you 1.58 grams per cubic centimeter for that ore. I want you to think about what that means in terms of comparison to something else. Density is really a comparison type number. So if you think back to the density that we had earlier, say for lead, it was 11.3 grams per cubic centimeter. So this ore is less dense than lead. This ore, however, is more dense than water, because water, you should know and really memorize, the density of water is 1 gram per cubic centimeter. So any object or any liquid or anything that it has a mass greater than 1 gram per cubic centimeter is going to sink in water, and any object that has a density less than 1 gram per cubic is going to float. And that's going to become a very important concept in some of the questions you're going to see on your assignment. So on the next slide, I have a picture, first of all, that shows you an example of how to find the density of something. You'll notice on the left-hand side, the graduated cylinder is around 600 mils. Put the piece of ore into the water level rose up by 200 mils. So if you wanted to find the density of this object, put it on a scale, find the mass. The scale picture seems to show 482.63 grams. Divide it by the volume of 200 mils, you could find the density easily enough. That's a visual I want you to have in your head of how you find the volume of an irregular shaped object. But this one here is even also important too. Notice the slide that I took from Google Images, the density tower as they call it. At the very bottom you'll see there's a bolt. You'll see a layer of honey and corn syrup. There's a popcorn kernel, maple syrup. There's a dice in there in the milk, you can't see it. There's milk, dish soap, cherry tomato, water, vegetable oil, some beads in there, soda cap, rubbing alcohol, lamp oil, and a ping pong ball. Your thing you have to take from this, your concept, is that the heavier the object is, the farther down it's going to go, and the lighter that is going to be at the top. So if you're given 4 substances and 4 different densities, the heaviest object will be at the bottom, and the lightest object will be at the top in terms of densities. And the same thing is shown this last slide, which is from your textbook. I believe it's around page 47, somewhere in the range. It's figure 2.5, and it shows you a diagram where it has 3 layers of liquids. Layer 1, the bottom, water in the middle, or layer 2, I guess is what they're calling it. On the top of water, there's another layer. There's also 3 solids, S1, S2, and S3. So if you're told the liquids are going to be ether, and the other liquid is chloroform, I believe, you would have to know what those values were to compare to which is on the bottom, which is on the top. So chloroform is heavy, 1.48, we did that earlier, therefore it's below water, and the ether is 0.917, or 714 rather, so it's above it. So you have ether liquid on the top, water is the next dense, and then the bottom is your most dense liquid. Then your solids, obviously the solid on top of the water is going to have a density less than 1 gram per cubic centimeter. And then it goes further on down with your other numbers. Each number compares to the one above. So S2 has got to be lighter than liquid 2, and S3 is going to be heavier than liquid 2, and so on. You should read the explanation in your textbook. It's quite nice, explains it very well, and you'll be able to answer the questions on your assignment about density. I hope this helps. Thank you.